Okay, so this is the homework solutions for complex numbers. So why do we do complex numbers? Well, for one thing, we're looking at the zeros of polynomials, and sometimes the zeros are real, which is where we have x-intercepts, and sometimes they are not real. But we still want to be able to figure out what those zeros, the complex zeros, are. So we need to know how to deal with complex numbers. So remember that I is defined as the square root of -1. So if you square I, you'll have the square root of -1 squared, which is -1. And if you have I cubed, you get, that's I squared times I. So we know I squared is -1. So you get negative I. And then if you have I to the fourth, you've got, that's I squared times I squared. But I squared is -1, so you get -1 times -1, which is +1. So those are the kind of things that you get when you raise them. The one that we deal mostly with is I times I, or I squared is -1. So that's what we're going to do here first. So we're just going to do the simple operations, which are addition and subtraction. So when you have addition or subtraction, you add or subtract the real parts. You add the real parts and you add the complex parts, and they're treated separately. So in this first one, you had 13 minus 2i plus -5 plus 6i. So you can kind of regroup things. So you have 13 plus -5. So those are the real parts. And then you have -2i plus 6i. And in this case, I is kind of like x in that we have each thing multiplied by I. So we just add the coefficients in front. So here we have 13 plus -5, which would be 13 minus 5, which is 8. And then we have -2 plus 6, or 6 minus 2, which is 4, and I. So that's the answer for the first one. The second one, we have 3 plus 2i minus 6 plus 13i. So one thing we could do is we could take those parentheses away for right now. And by doing that, I'm going to distribute that negative sign to both terms. So it's -6, -13i. Then we group the real parts together, and we can group the imaginary parts together, and then we can add the real parts, and we add the imaginary parts. So 2 minus 13 is -11. And then I could take that parenthesis away, so I'd have -3 minus 11i. So that's your answer for here. That's your answer for the first one. And the last one, the first one only has an imaginary part. Again, I'm going to distribute this negative sign, so I'll get -14 plus 7i. So negative times the negative is positive. Then we can group the real and the imaginary parts. The real parts together, the imaginary parts together. There is only one real part, so nothing happens there. And then we add these two. 13 plus 7 is 20. So you get 20i. Okay, next group. So these are multiplications. So it's like FOIL. So you do first, outer, inner, last. So if you do, I'm just going to write it out. So you're going to have 1 times 3, 1 times 3. So that's first. Outer is going to be 1 times -2i. Inner is going to be I times 3. And last is going to be I times -2i. So we can simplify things here. 1 times 3 is 3. 1 times negative 2 is negative 2. So we get negative 2i. Here we have I3, I times 3, which is the same as 3 times I. And then we have negative 2 times I squared. So you take the negative 2, move it out front, you have I times I. Then you convert the I squared into negative 1. So we said that earlier. So I squared is negative 1. And then it's just a matter of addition. So negative 2 times negative 1 is positive 2. Then we group the real parts together and the imaginary parts together. So 3 plus 2 is 5. Negative 2 plus 3 is plus 1. But we don't need to include the 1. So we just drop that. So we get 5 plus I. Okay, so that's the first one. Second one, same kind of deal. So you're going to do first, which is square root of 14 times the square root of 14. The outer is going to be the square root of 14 times negative 10i. The third part is going to be the square root of 10i. Actually, I think, well, if this were not the square root of 10i, then it would be easier to do the problem. So let's go ahead and change that. Well, we'll do it both ways. Let's just leave it in there, and then we'll fix it. We'll do it the other way just to show you. Okay, so you get square root of 10i times negative 10i. So that's last. So the first thing, square root of 14 times the square root of 14 is 14. Square root of, I think I left out a term. Let's go back here. I did leave it a term. So I did this one, but I didn't do this one. So we got one more term here, which is going to be square root of 10 times the square root of 14i. Probably should put the I with the square root of 10 here. Square root of 10i times square root of 14. Okay, now we'll figure it out. So the square root of 14 times the square root of 14 is 14. Next one we get negative 10 times the square root of 14i. We'll do this last one next, plus the square root of 10 times the square root of 14i. And then we get plus, so we get the square root of 10 times the negative 10 times I squared. So I take these two and multiply them together. So I squared is negative 1. And I'm not going to simplify these things because it's just about it. So this is going to be, I squared would be negative 1. So you're going to replace I squared with negative 1. Okay, now what I should have done, so this should have been, either this is the square root of 10, or this is either 10 or this is the square root of 10. So I don't know which one I want to do. They just have to be the same but different signs. So let's use plus right here. Okay, so now we're going to do that one, which I probably, hopefully, for the in-class people, I've told you to fix that. So in this case, what you end up with is the square root of 14 times the square root of 14. So that's first. Outer would be negative, it would be plus negative 10i times the square root of 14. Inner would be 10i times the square root of 14 So that's these two, and then you have positive 10i times negative 10i for the last. So the first one you get square root of 14 times the square root of 14, which is 14. This is the opposite of that in terms of sign. So you get negative 10 square root of 14 times I. Here you get positive 10 square root of 14 times. So those two cancel out. And then you have the last one, which is going to be 10 times negative 10 times I squared. So I squared is going to be negative 1. So replace I squared with negative 1. And so what you've got is 14. Here we've got 10 times negative 10, which is negative 100, times negative 1 is positive 100. So the answer is 114. Now these two are what we call complex conjugates of each other, such that the imaginary part, one's positive and one's negative. And what that happens, and the first parts are the same. The real parts are the same. The imaginary parts are negatives of each other. And what that allows you to do is it makes so the inner and outer terms cancel out, go to 0, and the last term is an imaginary versus times imaginary, but it gives you a real number. And so the final answer is a real number. Okay, and then the last one is this 4 plus 5i squared. So all that really is 4 plus I, 5i times 4 plus 5i. That's what squared means. So we use FOIL on this. So we'll get 4 times 4, that's first. 4 times 5i, that's outer. 5i times 4, that's inner. And 5i times 5i, that's last. So the first term is just normal multiplication, 16. Here we have 20i, and here we have 20i. So we multiply the two real numbers together here. So we get 20i, and then we have 25, 5 times 5 is 25, times I squared. Then we can change I squared into negative 1, so that's 25 times negative 1. And then we can add the two real parts together. 16 minus 25 is going to be negative 9, and 20 plus 20 is 40, so you get 40i. And there's your answer. Okay. So we've learned multiplication of just a normal two different imaginary numbers. Here we did the complex conjugate. Here we just did a square of a imaginary number, complex number. Okay, so here it says write the complex conjugate of the complex number, then multiply the number by its complex conjugate. So we did that in number 5. In this case, we're not given the complex conjugate. We have to figure out what it is. All it is the original complex number with the imaginary part with a different sign. So instead of plus 3i, it's minus 3i. Now we've multiplied this out. 6 times 6 is 36. 6 times negative 3 is negative 18, so we get negative 18i for outer. Inner we get plus 18i. And then we get 9. 3 times 3 is 9. Negative, we gotta make sure to put the negative in there. So we get negative, because we have negative times positive. 3 times 3 is 9, I squared. So these cancel out. So we're left with 36 minus 9 I squared, but I squared is negative 1. So that's going to be 36 plus 9, negative 9 times negative 1 is positive 9. So that's 45. So that's the neat thing about complex conjugates, is that you get a real number out of the whole thing. And it turns out that in zeros, complex zeros are always complex conjugates of each other. And they always come in pairs. So if I know one, I know the other. Okay, so here we go. Negative 3 plus the square root of 2i. Its complex conjugate is negative 3 minus the square root of 2i. Okay, so now we're going to use FOIL. So you're going to have negative 3 times negative 3, which is positive 9. We're going to have negative 3, so this is outer, negative 3 times negative square root of 2 times I. So I've taken negative 3 times negative the square root of 2 times I. Then I do inner, which is going to be plus square root of 2 times negative 3 times I. So you've got the negative sign, which goes there. You've got the square root of 2, which is there. You've got I, which goes there. And then you do last, which is going to be the square root of 2 times the square root of 2 times I squared. So this square root of 2, and there's a negative sign. Gotta do a little inventory here. So you get a negative sign from positive times negative. You get the square root of 2, the square root of 2, you get I times I. Okay, so the first term is 9, negative 3 times negative 3. These cancel out because you've got positive here, 3 times the square root of 2. Here you've got negative the square root of 3 times the square root of 2. Here we have negative, so negative, bring that down. The square root of 2 times the square root of 2 is 2. I squared is negative 1. So that's going to be 9 plus 2, which is 11. Okay, the square root of 8. So what is the complex conjugate of the square root of 8? Well, it's really just the square root of 8. Because if you think about it, I've got plus 0i. So this real number is just the real part plus 0 of the imaginary part. So if you multiply it by its complex conjugate, you're going to have the square root of 8 minus 0 times I. Well, all these parts is going to be 0 except for the first product. So you can have the square root of 8 times the square root of 8. That's first. Then you'll have outer, which is going to be, so you have plus square root of 8 times negative 0i. So this is 0. 0 times the square root of 8 is 0. Actually, I guess it's 0i, but 0i is 0. And then you get the inner, which is going to be plus the square root of 8 times positive 0i. And then you've got the last term, which is 0i minus times negative 0i. So all these things are 0 except the first term. So the answer is 8. That's the complex conjugate is just this, but you can, if it's 0, you don't have to include it in there. Okay, next one is complex numbers that are in the quotient form. So what you want to do is you want to rewrite it without a complex part to the denominator. So in all cases, you're going to take the number, the original number, you're going to put parentheses around the denominator. Then you're going to take the complex conjugate of that number and multiply both the numerator and the denominator by its complex conjugate. So what'll happen here is you'll have 2 times this imaginary. So you multiply 2 times each term. So you get 8 plus 10i. Now the denominator, you're going to have 4 times 4. The inner and outer are going to cancel out. So you have 4 times 4, and then you're going to have plus negative 5i times positive 5i. That's last. So we're going to have 8 plus 10i. 4 times 4 is 16. Here we get negative 25 I squared. So negative 5 times positive 5 is negative 25. I times I is I squared. Now, I squared is negative 1. So we'll get the numerator 8i plus 8 plus 10i. And then 16 plus 25 is 41. You have a negative times a negative. So that's your answer. Now, if you could simplify this, if there was some common factor in all of these, then you could simplify. But in this case, you can't. So that's the final answer. Okay, next one, same kind of deal. 3 plus I in the numerator, 3 minus I in the denominator. So you multiply by the complex conjugate of the denominator in both the numerator and the denominator. So in the numerator, you're going to end up with 3 times 3, which is 9. You'll have plus 3i plus 3i. So 3i plus 3i plus I squared, I times I. In the denominator, we have 3 times 3, which is 9. The inner and outer cancel out, and you'll have plus negative I times positive I. So in the numerator, we can combine the two imaginary parts. This I squared is negative 1, so let's just go ahead and make that substitution. So I squared becomes negative 1. So you have 9 minus 1, which is 8. And we have 3i plus 3i, which is 6i. And in the denominator, we're going to have 9. So what we have is 9 minus I squared. I squared is negative 1. So you get 9 plus 1. Negative 1 times negative 1 is plus 1, so you get 10. So we get that in the denominator. That's the whole purpose of multiplying by the complex conjugate, is to get rid of any imaginary things in the denominator. Now in this case, there is a common factor, which is 2, so we can divide each term by 2. And you get the final answer. So that's what we're looking for. Looking for a rational result that does not have a complex denominator. Okay, and the last one, we have 8 plus 16i. The denominator says 2i, so that's 0 plus 2i. So the complex conjugate is going to be 0 minus 2i and 0 minus 2i. Now I could have just put in negative 2i. So in the denominator, you get 0 times 0, which is 0, 0 times 2i, which is 0, 0 times negative 2i, which is 0. So the only thing that we have left in the denominator is 2i times negative 2i. In the numerator, we're going to have 8 times 0, which is 0, 16i times 0, which is 0. Then we're going to have 8 times negative 2i. And we're going to have 16i times negative 2i. So we get two terms, because this 0 gives you just a 0 result. Okay, so then we have 18 minus 2i, so it's negative 16i. We'll have 16 times negative 2, which is negative 32i squared. 16 times negative 2 is negative 32. I times I is I squared. In the denominator, we have negative 4i squared. So 2 times negative 2 is negative 4. I times I is I squared. But I squared is negative 1. I squared is negative 1. So in the numerator, we'll get negative 32 times negative 1, which is positive 32. Put the imaginary part second, negative 16i divided by positive 4. So then we can divide, those have a common factor of 4. So 32 divided by 4 is 8. 16 divided by 4 is 4. So that's your final answer. Okay, so that's how you write them in standard form. Okay, and the next one is looking at how you combine rational expressions with imaginary numbers. So you have to find a common denominator, and in this case the common denominator is the product of the two denominators. So we're going to take the first term and multiply by the second denominator. So you take the first denominator and multiply by the second denominator, and we're going to take the second denominator multiplied by the first denominator. And we do that in both the numerator and the denominator so that we're multiplying effectively by 1. Okay, so let's multiply this stuff out. So here we can just distribute the 2i to each one of those. So you'll get 2i times 2, so that's this first product. Then you'll get negative I times 2i. So negative I times 2i. Okay, so that's the first. Now I'm going to put this in one denominator because you're going to have, you can see I have the same denominator, and doesn't matter which one I put first. Okay, now the second group you're going to have 5 times 2, which is 10, and 5 times I, which is 5i. So we get 5i of the second one. So these are the two numerators combined, common denominator. Now here you can see I have this complex conjugate situation. So these are complex conjugates of each other. But let's go ahead and do the numerator first. So you're going to have 2i times 2, which is 4i. Here you're going to have negative 2i squared. So you get negative 2i times I is I squared, plus 10, plus 5i. And in the denominator I can multiply this out. So I'm going to have 2 times 2, which is 4. 2 times 2, which is 4. The inner and outer cancel out. I'll have negative sign, and I'll have I times I, which is I squared. Now in the numerator I can combine the, well, let's change I squared to negative 1. Okay, negative 1 times negative 2 is positive 2. Positive 2 plus 10 is 12. 4i plus 5i is 9i. And then the denominator I have 4 minus I squared. I squared is negative 1. So you get 4 minus a minus 1, which is plus 1. So you get 5. So you get 12 plus 9i over 5. So just double checking here. Make sure I didn't do anything wrong. Yeah, I think that's right. Okay, next thing, quadratic formula. So what's going to happen here? Doesn't necessarily have to happen, but we'll end up with a negative square root of a negative number. So we have to convert that square root of a negative number into some I, involving I. So we want the two complex roots of this equation. So in the first one, A is equal to 1, B is equal to negative 2, C is equal to 2. So the quadratic formula is x, which are the values of x that cause us to go to 0, are minus b plus or minus the square root of b squared minus 4ac all over 2a. So all I have to do is plug in the values. So you have negative b plus or minus the square root of negative 2 squared minus 4 times a, which is 1, times c, which is 2, all divided by 2 times a. So here I'll have a negative times a negative, so it's positive, plus or minus the square root of So you have 4 minus 8. So that's negative 4, all divided by 2. And then we could write that as 2 plus or minus the square root of negative 4, or square root of 4, times the square root of negative 1, all divided by 2. But the square root of negative 1 is I, so we get 2 plus or minus the square root of 4, which is 2, times I, divided by 2. And then you can simplify because each one of these is divisible by 2, so you get 1 plus or minus I. So the two solutions are this. The factors would be x plus 1, well, yeah, so actually it's x minus, so it'd be x minus the quantity 1 plus I, and the second one would be x minus 1 minus I. So this is going from the zeros to the factors. So one of the factors is plus, one of the factors is minus. You know, this equals that, so to solve for 0, I would subtract this from both situations. Okay, so the next one, A is equal to 16, B is equal to negative 4, C is equal to 3. So we get x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So you get x is equal to minus a negative 4 plus or minus the square root of negative 4 squared minus 4ac, or ca, all divided by 2 times a. So negative of a negative is you get positive, so you get 4 plus or minus the square root of negative 4 squared is positive 16, and then here we get negative, so we get 12 times 16, or 4 times 48, whatever that is. So we'll get our calculator out for that. So we have 3 times 4 times 16, 192. Okay, so I have minus 192, all divided by 32. So we get 4 plus or minus the square root. So 192 minus 16 is 176. So minus 176, all divided by 32. I get 4 plus or minus the square root of negative 176, well no, the square root of 176 times the square root of negative 1, all divided by 32. And so that becomes I over 32. Now the only way we could simplify this is if this is some multiple of 4. So if you take 176 and divide by 4, you'll get 44. Now actually what I wanted is if this is some multiple of 16. 176 divided by 16 is 11. Okay, so you get plus or minus the square root of 11 times the square root of 16 times I divided by 32, but the square root of 16 is 4, so you get 4 plus or minus the square root of 11 times 4 times I divided by 32, and you can see I can divide every term by 4, so I'll have 1 plus or minus the square root of 11 I divided by 8. So that's the simplified version. So, you know, I got to this point and I saw that you could divide 32 by 4. So if I could somehow get a 4 out of here, well, to get a 4 out of here, I have to have a multiple of the square of 4, which is 16, so that I can break 176 up into 11 times 16. So then the square root of 16 becomes 4. And now I have 4, 4, and I can divide that by 4. So I take this divided by 4, which is 1, this divided by 4, which is 1, so I get 1 times the square root of 11. And then I divide by 32 divided by 4. Okay, so the last problem is 16. And what I'm going to do is I'm going to convert this. I'm going to multiply everything by 10. So 1.4 will become 14. 2 times 10 is 20. And 10 times 10 is 100. Why did I do this? Just, it has the same zeros because I could factor the 10 back out. But it's going to have, it's just easier to deal with whole numbers or integers. So I'm going to have A is 14, B is negative 20, C is equal to negative 100. So using the quadratic formula, minus B plus or minus the square root of b squared minus 4ac over 2a. So we have negative and negative 20 plus or minus square root of b squared, which is negative 20 squared, minus 4 times a, which is negative 100, times a, which is 14. And this actually is just going to be, there are no complex roots to this particular one, just because I can see here that the argument is going to be positive. So you get 20 plus or minus the square root of 400. So that's 20 squared. And then I got to multiply those last three numbers together. So get our calculator out. So we have 4 times 100 times 14. So that's 5,600. All divided by 2 times 14, which is 28. And so if we add 400 to 5,600, we get 6,000. Now, what we can do is see if we can, what's a common factor here amongst these two? Well, 4 is 1, so I can divide both of these by 4. So what I'm looking for is 6,000 divisible by 16, because I want to get the square root of 16, so I can use that. So if we take 6,000 and divide by 16, we get 375. So this is going to become 4. So we can divide them all by 4. So you'll get 20 divided by 4 is 5. 4 divided by 4 is 4. And 28 divided by 4 is 7. Now we should be able to simplify this a little bit further, because I think if you take 375, you can divide by 25. Okay, so 375 is 25 times 15. So the square root of 25 is 5. That's why I chose 25. So we get 5 plus or minus 5 times the square root of 15 over 7. So my two zeros are going to be That's what they're asking, weren't they? Use the quadratic to solve. Okay, to solve it. So that's the solving is doing the zeros. So our two solutions are x equals 5 plus 5 times the square root of 15 over 7, and the other one is 5 minus the square root of 5 times the square root of 5. 5 times the square root of 15 over 7. And let's go ahead and figure out what those are. 5 plus 5 times the square root of 7 divided by the square root of 15, sorry. Square root of 15, so divide by 7. So we get 3.48, and the other one, we subtract that, 5 times the square root of 15, and we divide by 7, and we'll get negative 2.05. So let's plot this thing and see whether the zeros, so to find the solutions of functions, one thing you can do is you can plot the polynomial. So let's go back and figure what that was. So the original polynomial is this. So we have 1.4 x squared minus 2x minus 10. So that's y equals that. So to set y equal to 0, you find the solutions. So we graph that, and you can see there are two x-intercepts. And if we did this right, those two x-intercepts are what we got. So over here, it looks like it's negative 2 point something, and over here it's positive 3.5. So you can see that's, if I zoom in closer, I can find the exact value. This is 3.48. So apparently I did it right. So that's good. Here, I just, using what we talked about early on, I squared is going to be negative 1. I cubed is negative I. So for 17, I'd have 4 I squared, but I squared is negative 1. And then I'd have I cubed, which is negative I. So I'd have negative 4, and then negative times the negative is positive. So I get 4 plus 2i. So anytime you have a higher power of I, you can simplify it. Now the second one, what you would have here is you'd have the square root of 75 times the square root of negative 1, the whole thing cubed. So then you'd have, you could replace negative 1 with I, so you get square root of 75i, and that would be the square root of 75 cubed, and that's equal to, and then times I cubed. But I cubed is negative 1. So that's negative I, sorry. So I cubed is negative I. Now if you take the cube root of 75, what you could do here is, I don't know if this comes out to be let me use your calculator. Square root of 75, let's just use the calculator first. So you take the square root of 75, and then you cube that, and you get, you don't get anything that's simplified. So so what you get is negative the square root of 75 cubed I. So that's simplified. Doesn't look that simplified. Just think about this. 75 is equal to 25 times 3. So you're taking that and then you're cubing it. The square root of 25 is 5, so you'd have negative 5 times the square root of 3, the whole thing cubed times I. And then you could cube each one of those, so you get 5 cubed times the square root of 3 cubed I. Then you'd have negative 5 cubed, and then you'd have square root of 3 squared times the square root of 3 I. But the square root of 3 squared is 9, so you'd end up with 9 times 5 cubed times the square root of 3i. And if we multiply all that out, 9 times 5 cubed is 1025. So you get negative 1025 square root of 3i. And let's just check this out. If you take this 1125 times the square root of 3, just in decimal, you get 1948 point something. And if I go back here to this point where I haven't simplified things, so if I take the square root of 75, so the square root of 75, and then I cube that, I should get 1948 if I did it all right. Something's wrong. Square root of 75 cubed, I get 649. Okay, so what did I do wrong here? 5 cubed, 125. 125 times 3 is, oh, it's right here. That should not be that. So you get, what you get is square root of 3 squared is 3, so it's 3 times that. So you'd have 3 times 125, which would be 375. Okay, and then that works out. If you take 375 times the square root of 3, you should get the same number. Yep. So that's the original unsimplified version. That's the simplified version. Not a big difference. Okay, and then the last one, you've got 1 over 2i cubed. So what you'd end up with is 1 over 2 cubed times I cubed. And 2 cubed is 8. And I cubed is negative I. So you'd get negative 1 over 8i, but we don't want to leave it that way. So we're going to multiply by the complex conjugate of 8i, which is going to be negative 8i. So we do that in both the numerator and the denominator. So these negatives cancel out. So you're going to end up with 8i in the numerator. And then the denominator, we're going to have 8 times negative 8 times I squared. 8 times negative 8 times I squared. So you get 8i over, so I squared is negative 1, so this ends up being negative times the negative is a positive, so you get positive, and then you get 8 times 8, which is 64, and then you can divide both those by 8, and you get I over 8. So that is the simplification of that. Make sure I get all that right. So this negative goes there. I cubed is negative I. Multiplied by the complex conjugate of 8i, which is negative 8i. You'll get 8 times 8, just change the sign, positive 64. This negative times that negative became positive. So I think that's all right. Okay, so that's it. Okay, so the last two problems are find the complex solutions of the quadratic equation and the factored version of the original equation. So we want to find the values of x which make this go to 0 and also to make it into a factored form, the same way with the second case. So we use completing the square. So to do that, we take 8 divided by 2, square it, which is 4, squared, which is 16. So we add 16, and we subtract 16. And then we take the first 3 terms and make that into a complete square. So we use this number 4 here. 65 minus 17 is 49. Not a coincidence, because the square root of 49 is 7. Okay, we subtract 49 for both sides. Take the square root. So we get plus or minus the square root of negative 49. And the square root of 49 is 7. So that'll become x plus 4 is equal to plus or minus 7i. Square root of negative 1 is I. Square root of 49 is 7. We subtract 4 from both sides. And so we have 2 solutions. X is negative 4 plus 7i, and x is equal to negative 4 minus 7i. And if I plug those into my original equation, which was x squared plus 8x plus 65, it'll get 0, either one of those. Now the factored version, so the factored version of the original equation, x squared plus 8x plus 65, is x minus the quantity negative x plus 7i times x minus negative 4 minus 7i. So you take x minus the 2 zeros. And if I multiplied this out using FOIL, I would get x squared plus 8x plus 65. You could also write this as x plus 4 minus 7i. So I'm just distributing this negative to both of these terms, and then you'd have x plus 4 plus 7i. So either one of those is okay. I would just leave it in the form like this, the original one. Okay, next one. Okay, number 21. Same deal. We need to complete the square. So you take negative 16, yep, divided by 2, square it. Negative 16 divided by 2 is negative 8. Square that, you get 64. So we're going to add 64 here, and we're going to subtract 64 there. Now you can make this into a complete square, which is going to be x minus 8 quantity squared. So if I multiply this out, I'll get that. And then I have 88 minus 64, which is 24. And then I subtract 24 from both sides. So I know I'm going to get complex solutions because this is negative. You take the square root of both sides, so you get x minus 8 plus or minus the square root of negative 24, which is plus or minus the square root of 24i. But we can rewrite this because the square root of 24 is the square root of 6 times 4, which is going to be 2 times the square root of 6. So this is x minus 8 is equal to plus or minus 2 square root of 6i. And then if we add 8 to both sides, we'll get the solutions x is equal to 8 plus or minus 2 square root of 6i. Or x equals 8 plus 2 square root of 6i, and x equals 8 minus 2 square root of 6i. And finally, the factored version. Well, before we do that, if you plug these numbers, these complex numbers, into the original equation, x squared minus 16x plus 88, you will get 0, because those are the zeros. Now, there are no x-intercepts because this is a complex number, but you do have zeros. And then to rewrite the original expression, x squared minus 8x plus 88. Is that right? Or is it 16? 16. So the way you write that as a factored form is you'd have x minus the quantity 8 plus 2 square root of 6i, and x minus 8 minus 2 square root of 6i. So this matches up with that parenthesis. This one matches up with that one. And if you multiply these two together, you'll get x squared minus 16 plus 88. Or again, you can distribute the negative to both of these. So you have 8x minus 8 minus 2 square root of 6i times x minus 8 plus 2 square root of 6i.